All right, so we're going to be talking about more of Leonard Susskind's statistical mechanics course. Again, if you're interested in this kind of material or in this kind of style that I present physics in, please subscribe to this channel and visit my Patreon page. I take it that you have decided to visit my Patreon page at this point because this is going to be one of my first videos that I'm putting on that page instead of the YouTube page. This is again a course on a mini course, if you will, on statistical mechanics as it was taught by Leonard Susskind and modified by myself, so that it is shorter and perhaps a little bit easier to follow without him asking or answering questions from people in his audience. As you know, if you've seen his videos, they are long. They're approximately 2 hours long each. I think he's got like 10 courses on this. And so I've decided that I have gone through all of it, and I've distilled it down into a way that I find it easy to understand and easy to follow. Without further ado, let's get right into the actual materials. So before we had talked about what probability distributions were, now we're going to talk a little bit more about a very important quantity in statistical mechanics that's going to help us later on understand how we can mathematically understand ideas like entropy and energy. Anyways, so let's get, again, I'm repeating myself a little bit, but let's get right into this. So we have, so we want to understand the number of states that a system has in terms of probabilities, right? So this is actually going to be very interesting to look at. Again, I'm just looking at an example here where we have a coin, 2 coins actually, 1 coin. So in our first state, we have heads, heads. Our second state is heads, tails. Third is tails, heads, and tails, tails. And we've talked a little bit about how 2 and 3, states 2 and 3, could be thought of as the same unless you mark one of the coins, right? So this is the test of indistinguishability or distinguishability. And if we're going to assume that these things are distinguishable, then we have a one-fourth probability, or a 25% chance of having any one of these states occur. And this is what our probability distribution looks like. Okay? This is going to help us because let's take a look now at what a probability function actually is. So a probability function is associated with a particular state, right? So heads, heads. Yeah, there's a particular probability that you will get heads, heads in this case. And in this case, that's 1/4. So the input to this function is a state, right? And you output a number. So the probability function links the real world, if you will, states that you observe in the real world, to numbers, right? Numbers, I love to think of these as mappings, right? So you have these states in the real world. Right, so states, and you input them into this probability function, and you output something in R. Okay, this is a very general way of thinking about these things, these probability functions, because later on, it might be interesting to understand, well, what happens if we, instead of this being an R, being a number, it's perhaps a vector, maybe a tensor or something like that. That would be something very interesting to look at, but not necessarily something that would be interested in right now for the brevity of this course, or for the brevity of this course. Anyways, this is what a probability function does. It takes a state and it assigns a number to that state, and that number is associated with how likely you are to observe that state. Okay, this goes all the way into biophysics also. Proteins have different types of conformational states, and these conformational states can be associated with some number or some energy, right? And that's going to also be very important, that there's going to be an energy associated with this number, right? So with this number, we're going to have some energy associated with it. Anyways, as we've said before, that this energy, or this probability distribution, each one, right? So we said that the sum of all of these has to equal 1, right? So the sum of all the probabilities, which is the probability of getting heads, probability of getting heads tails, probability of getting tails heads, and the probability of getting tails tails. Each one of those is 1/4, as we've seen in this probability distribution, okay? And so we take 1/4 plus 1/4 plus 1/4 plus 1/4, and that gives us 1. So this is a general principle that all the probabilities for a particular system have to add up to 1. Okay, this is just because what this statement says right here is that the probability that you will observe any of these states is 100%. That's what this 1 means. Okay, 1/1. So let's generalize this a little bit, because this is going to actually be very interesting. It looks like I'm taking this out of the blue here, but let's follow this really quick. We're introducing now a log of the probabilities. Okay. So the probability, again, I'll write this out. This is going to be right here. This is going to be 1/4 the probability of heads plus 1/4, actually, to be even more general, and I'll do this in black. To be even more general, we have the probability of heads times the log of the probability of heads. Okay, this looks a little bit redundant, but hear me out on this. Then we're going to have plus the probability of heads tails times the log of the probability of heads tails, plus, and so on. So what does this become? Well, this here is 1/4. This here is 1/4. Okay? So what we have is that we have 1/4 of log of 1/4. Log of 1/4, plus 1/4 of log of 1/4, and so on. So this is essentially 4 times the log of 1/4. Essentially, all of these 1/4 will go away. Okay? So we've eliminated now. Well, that they don't go away. This is 1/4 of the log of 1/4 times 4, essentially. It's times 4. It causes them to go away, right? So we just get the log of 1/4. Okay? Well, what is the log of 1/4? That's, if you know a little bit of math, that is the negative log of 4. And this 4, right, this is the number of states that we have, right? Because if we go back to the original system here, we have 1, 2, 3, 4 states. So this is very interesting. This is very interesting because now we can say for any system, here we have it here. My apologies for my computer in the background if you can hear it. Anyways, for any system, we have that this here, what we started with, without the minus sign, so the minus sign's actually right here, but this is what we started with, is equal to this, right? The log of m, where m is the number of states, right? What is this? So we have probabilities on this side of the equation, and we have the number of states on this side of the equation. We have essentially found out an equation for the number of states of a system, the number of states of a system, in terms of probabilities. That's why this log is right here. And then we had the original negative right here, we just moved the negative over here. Right? This is a very, very important quantity. What you usually see in statistical mechanics is people really just jump to this and they say that this here, what we have on the right hand side, is equal to S. And they tell you, okay, what's S? Right? S is given by the log of m in some general sense, right? What we'll see is that this here takes a very similar form of something called Boltzmann's equation or Boltzmann's law. This is what's engraved on Ludwig Boltzmann's tombstone in Vienna, and this is it's very important to understand how this comes about, right? So let's take a look at this really quick on visually, right? So essentially, the log of m, what's the log function look like? Well, the log function looks like this, right? So this is our log function. As we increase the number of states, right? So say we have 500 possible states. Say we're conceptualizing a system or a protein system, right? So proteins can take on multiple different states. And these multiple different states can be associated with some energy or whatever, but suppose we had 500 possible states in our system. If we have 500 possible states in our system, how can we understand the probability of each one of these systems, or how can we understand the probabilities of each one of these? Well, we use this equation, right? But again, if we have 500 states in our system. Here's our 500 on our log axis, or m, right? So m is the number of states in our system. This is what the log function looks like. Right? It passes through 1 like this, and assigned to it is going to be some number, right? So if you put log of 500 in here, or if you type in your calculator log of 500, it's going to give you about 2.7, right? So this thing, this 2.7, is a measure of the number of states, right? And this measure increases, not exponentially, it actually increases very slowly. It starts to, you can see that the slope of this curve, if you were to draw a slope here, it's somewhat steep here, but it gets less and less steep as you traverse across m, right? And what this means is that we have a number, essentially, a number here, or this number, which as it increases very slowly, we're accounting for ever increasing changes in the number of states of our system. And the beauty about the log function is that we're dealing with small numbers, right? It's still increasing, but it increases slowly, and it's a very good measure of accounting for large numbers of states, right? Here I just picked 500, but plug in log of 1,000, right? And you get a number that's easy to deal with on your calculator. And this number is directly associated with the probability of each state that can occur, okay? So what does this mean, right? So if we go back, we're summing across here, right? So I in this case goes to 4, right? So I in this case will go to 4. So that means if we actually generalize this correctly, or more completely, what I didn't add here is, I'll get rid of this really quick, and we have an m right here. Okay, so what this is, again, is a measure of the number of states in a system. And this is going to be very important in understanding what entropy is. Entropy is a measure of the number of states that a system can have, okay? And as that number of states increases, we can understand that in terms of the probabilities here, this very, very foundational important equation. Okay, so this is video number 2 of Statistical Mechanics by Leonard Susskind. If you enjoy this type of material, then please subscribe. Again, visit my Patreon page, and I guarantee you won't be disappointed in the type of topics that we'll be covering for the rest of this playlist. So I'll see you guys in the next one. Bye.